Okay, continuing where we left off with part 2 of the lesson of 8.4, we had just begun to look at the decomposition for this second problem. And what you would have to do as you continue with this partial fraction decomposition is first multiply everything through by the LCD, namely x squared times x minus 4. The left side works out very nicely to 2x squared minus 12x plus 4. A over x, when you multiply that LCD there, one factor of x will go away. You'll have ax times x minus 4 plus, here both x squareds are going to cancel out. You'd have b times x minus 4. Finally, for your last fraction here, the x minus 4's cancel. And you'll have c times x squared. You have to find an a, a b, and a c. And I think most students would realize that plugging in an x value of 4 and an x value of 0 would be good, would be very effective. The problem is you're going to have to find three variables, three constants I really should say, and that would require that we plug in three distinct values of x. You certainly could also plug in a friendly x value such as 1 and find your other missing variables, and that's fine. But I'd like to show you something called coefficient analysis. Coefficient analysis says, in essence, let's multiply everything out on the right side. We'll have ax squared minus 4ax plus bx minus 4b plus cx squared. And then I'd like for us to add our like terms together. Now, of course, right now, as you're looking at ax squared plus cx squared, we don't know what a or c are, so it's not like I can just add numbers like 2 and 3 to get 5. That being said, if I have ax squared plus cx squared, I could actually factor out an x squared from both of them, and in essence have a plus c in front of x squared. Looking at what we have in front of x, we have a minus 4ax and a plus bx. In a very similar way, I could factor out an x. But I'm going to put my b first, just so it starts off as a positive value. We'll say plus b minus 4a, put our x there. And if you want to distribute that x back in, you can see more or less that that's exactly what you have. Then we'd be left with a minus 4b. Now, right now, this might not seem to be very helpful at all, but this is something called coefficient analysis. If a quadratic is equal to a quadratic, the coefficient, the number in front of x squared, should equal the number in front of x squared on the other side. Right here, a negative 12, whatever's in front of x, should match up what's in front of x over here. And finally, the constant should also be the same. So this is a method that can help you in advanced courses as well. You might see it creep into differential equations every once in a while. But what this means is a plus c would have to equal 2. That b minus 4a would have to equal negative 12. And then very nicely, negative 4b would equal, plain and simply, just a 4. So this other method, it's important to see it. Solving this very last equation, you'd get b equals negative 1. Then if we take that mid equation, the middle equation, b minus 4a equals negative 12, let b equal negative 1. How about we add a 1 to both sides? And negative 12 plus 1 is actually negative 11. And when we divide by negative 4, we'd get 11 fourths. From here, looking at a plus c equals 2, knowing that a now is 11 fourths, 2 is actually 8 fourths, if you'd like to change that. And if I subtract 11 fourths from both sides, I'd be left with negative 3 fourths. Now, what's nice about this is looking at this decomposition, a over x plus b over x squared plus c over x minus 4, you have to realize this is what our new integral is. My a is 11 over 4, so I get 11 fourths all over x. I'll say plus b, now my b happens to be negative 1, that's negative 1 all over x squared. My c is negative 3 fourths, and I'm going to put that all over x minus 4. So here's this problem that looked very, very bad, and thank goodness it's actually coming together rather nicely. It's turned into 3 distinct problems that we're going to be able to break down, hopefully pretty fast. Let's finish that up. This would become 11 fourths times the integral of 1 over x minus the integral of 1 over x squared dx. Got to put those dx's in. And then we could say minus 3 fourths the integral of 1 over x minus 4 dx. So just pulling those numerators, those coefficients out in front. Let's finish this up. We'd get 11 fourths. This becomes the natural log of the absolute value of x. Be careful. 1 over x squared is really just x to the negative 2. Here's where I can just reverse that power rule. Bump my exponent up by 1, so it'll become x to the negative 1, and then divide by negative 1. So really I have a minus and a negative. That turns into plus. But x to the negative 1 is really 1 over x. There's no natural log in this last antiderivative. Then we'll say minus 3 fourths ln of the absolute value of x minus 4. Don't forget you want to say plus c for a constant. Well, at this point, we're done with this problem. An integral that looked to be incredibly difficult, very, very brutal, actually can be doable once you decompose it. Okay, as we look at the second page of the notes, you're going to see that anything with a quadratic factor, anything with x squared plus either a term of x or a constant, will be skipped. That's not covered on the AP exam. Thank goodness we're not going to cover that in class either. But what I do want to close with is example 5. Example 5, we have 3x to the 4th plus 1 all over x squared minus 1. At first you might wonder, well, wait a minute, shouldn't we skip this also? You just said that if you had a quadratic factor, we're not going to bother with that. And I'm looking at that x squared minus 1. Here's a quadratic. But that x squared minus 1 factors into linear factors, x plus 1, x minus 1, and that's something that we can work out. So when I said we can't deal with quadratic factors, they're unfactorable quadratic factors. What you do have to realize for number 5, though, is that the degree of the numerator is actually higher than the degree of the denominator. And when you see that, you're going to have to do long division. Now, long division, you're going to have placeholders. As some teachers call them, they call them ox terms because a 0 goes in front of the x. And so we'd have 0x cubed, 0x squared, 0x, and a plus 1. Out in front, you could have x squared. You could even put in an ox term here if you would like. That would definitely be an option. But remember, with long division, we first play the matching game, where we'd say, what times x squared would match to 3x to the 4th? And the answer would be 3x squared. And then we're going to multiply 3x squared everywhere. So we'd get 3x to the 4th plus 0x to the 3rd. 3x squared times a minus 1 is a minus 3x squared. Then, just as you did in long division in elementary school, you would subtract, but subtracting is really adding the opposite. So in red, I'm just changing the sign, making that the opposites. And then when we add, you can see actually 2 terms cancel out. When two terms cancel out, you can bring down two terms, and that can help you out time-wise. Then, at this point, we're going to play the matching game one more time. Very repetitive process. What would you multiply to x squared to get 3x squared? Well, the answer would be plain and simply a 3. And then you'd have to distribute that 3 everywhere. You'd get 3x squared plus 0x minus a 3. Once again, you're going to change all these signs. And 1 plus 3 is actually a 4. So with this remainder, what we generally do is we'd write plus 4 over x squared minus 1. So this integral, and we're not even going to finish it. We didn't finish it in class either. But now this integral that looked very, very difficult can be rewritten as the integral of 3x squared plus 3 plus 4 all over x plus 1x minus 1. The 3x squared and the 3, you know the antiderivative of. This last fraction you're going to have to do much the same way we did in example 1 with a partial fraction decomposition. But really that wraps up our lesson on partial fractions.